When a mass is placed at a particular height, gravity attracts on it, and we call that as gravitational potential energy. The gravitational force, right? The force experienced here is because of gravity, so it is known as gravitational force. So if we want to escape Earth's gravitational field, we have to have at least the energy that is equal to binding energy. Orbital velocity is the velocity of a satellite around planet Earth. So how fast it is revolving or rotating around that particular planet. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. We were discussing about gravitation. So let's see what gravitation holds for us today. So today we are going to discuss about what is gravitational potential energy. We all know that potential energy U just means that it is the energy possessed by an object due to its position or configuration. In this particular case, we are talking about gravitational potential energy. So what exactly is this gravitational potential energy? Sir, it is very simple, sir. When a mass is placed at a particular height, gravity attracts on it, and we call that as gravitational potential energy. Well, you're actually right, and if you put it into a sentence, you can actually frame it much better. So we can actually say that the definition for gravitational potential energy can be defined as the energy possessed by an object when placed in a gravitational field. So we can say that gravitational potential energy is nothing but the energy possessed by an object when it is placed in a gravitational field. For example, I can say that if this is Earth, if I keep anything close to Earth, let's say this is the moon. If I keep anything close to Earth, then it will automatically feel an attractive force towards the Earth. Actually, there is a force of attraction between these two masses. So since Earth is the bigger body, this moon will feel an attractive pull towards Earth. So this particular phenomena, this particular energy possessed by that moon, since it is kept in Earth's gravitational field, is known as gravitational potential energy. Again, the field is just in the sense that, okay, where up to which point can Earth influence that particular material? That particular distance is known as its field strength. How much can this particular body influence other body gravitationally? Then that is its gravitational field. But sir, still what is gravitational potential energy and where it is coming from? Because, okay, if anything is placed in a gravitational field, it will create gravitational potential energy. But what about Earth? Earth has a gravitational potential energy. We don't know exactly where it is coming from, right? But we do. We do have a mathematical explanation for what is gravitational potential energy. So, to define that, let's use a simple case. Let's imagine that I am trying to bring something which is infinitely far away. We just say infinitely far away for mathematical concerns. Let's say something that is really far away, and I'm going to bring that particular object towards the center of the Earth. Okay, I'm going to bring an object, let's say an asteroid, Halley's Comet or something. I'm going to pull that and bring it to Earth's center. So, technically, from infinite distance away, I'm going to pull a mass. Let's say it's a unit mass, or let's say it's mass m. I'm going to bring mass m, which is infinite distance away from Earth. I'm going to bring it close to Earth or to the center of Earth. So again, to bring this particular mass from infinity to a particular point, I have to do work, right? I have to carry this load from infinity and I have to push it and keep it near Earth. You can also imagine the reverse also. It'll also be true. That is, if I take one particular mass and if I have to push it back to infinity, I have to do work, because during the entire time, Earth will be trying to pull it closer. Earth will be saying, okay, my gravitational force is really strong. I have to have this. I'm going to pull it back. Then I have to say that, no, I have to give it to infinity. So then you have to take it to infinity. You can imagine either cases, both are mathematically true, only the sign will actually differ. So again, if I'm bringing this particular mass from infinity to a particular point, I have to do a certain amount of work. So this certain amount of work is actually stored as potential energy of that particular system. In earlier cases also, I told you that the work we are doing is actually stored in as potential energy. So in order to calculate the gravitational potential energy or potential energy of a system, we just calculate the work done in bringing a unit mass or anything from infinity to a particular point. Then we can calculate the work done. That particular work done will be equal to the stored potential energy of the system. So we are trying to find what is gravitational potential energy of Earth. So again, we are bringing a mass from infinity to a particular point. So again, it is going to vary, right? Because if I'm taking a mass from Earth and moving it to infinity, the force I have to apply initially will be very high because the Earth is pulling on it, right? Earth is pulling on it. As I move further and further away, I don't have to apply that much force. So it's a variable force since the pull will become weaker and weaker. Again, in this particular case, if I'm bringing the mass, then automatically as I get closer and closer, I have to hold down to the mass so that Earth doesn't pull it, right? So I have to apply some force to keep that in place. So the point is that the force is actually a variable force. So we have to account for that and use the equations for variable force. That's it. We do know that work done is equal to integral f dx. Why integral f dx? Because it is a variable force that is doing the work. That is why it is integral f dx. At every point, the force may be succumb to change. That is why we are using integral f dx. So next we have to apply the limits, and let's say we are bringing the mass from infinity to a surface point on the Earth. Let's say that is r. So I'm going to bring the mass m from infinity to a particular point r. So I'm starting from infinity and I'm ending at point r. So I'm doing the integration from infinity to r. Then I can actually see that, okay, this is the lower limit, this is the upper limit, and this is the varying quantity. Then we can go on and do our integration. So again, f dot dx. So again, what is f? F is nothing but the gravitational force, right? The force experienced here is because of gravity. So it is known as gravitational force. So we can say that, okay, Fg will be equal to G capital M, that is mass of the planet, into small m, that is the mass we are bringing, divided by r squared. R is nothing but the distance between these 2 points. You can also take x. Since we are taking dx here, then we have to take x. So this particular equation should be written down as G capital M small m divided by x squared. Again, x is the distance between these 2 points. Okay, x is the distance between these 2 points. The changing displacement or change in distance is indicated by x. So force, we have an equation. Now we are going to substitute this particular equation into this derivation. So we get the equation as integral infinity to r. Instead of f dot dx, we are going to write g m divided by r square. And if anybody has any confusions about f dot dx, where is the cos theta? We are just assuming that, okay, force and displacement are along the same line. So theta is approximated to 0 degrees. That is why we don't take cos theta here. Again, you can take cos theta, there is no other problem, but the equation will become more and more complex. So we just take an ideal case where, okay, the force applied is in one direction and the displacement happening is also in one direction. So that is why we take cos theta as 0 degrees, if anyone is wondering about that. Again, so when we integrate this particular quantity, what do we get? The only result we do know is that integral x raised to n is equal to x raised to n plus 1 divided by n plus 1. That is the only result we know about integration. So, okay, let's begin our integration process. It's very simple. Again, we know that integral symbol only operates a changing quantity, and the only changing quantity here is the x square. So this is an x square, not an r square. You can take r square or x square, it is completely fine. This signifies the change in distance. Since we are taking dx or dr, both are fine. If any confusion is there, I'm going to take dr here. Then the problem will be solved, right? So I'm going to take distance as dr instead of dx. That is small change as dr instead of dx. So I can take r square here. There is no problem. Even if you take r square, x square, it does not matter because it means distance. So you can take any quantity you want. So again, gmm by r square. We know that it only integrates which is a changing quantity. So g is a constant, which is gravitational constant, which comes right outside of the integral sign. Mass of the planet, it is not going to change. So m is also coming right outside, and mass which we are bringing, just because we are bringing in doesn't mean the mass is going to change. And we are bringing it very slowly actually. Mathematically speaking, I can say that I'm bringing this particular mass without any acceleration. So I'm not producing any acceleration, I'm not changing any velocity. At infinite time, I'm bringing it very slowly. So I can say that, okay, I'm not producing any acceleration, so the mass is also not changing. So gmm is not changing. Is the distance changing? Yes, the distance from infinity to earth is changing at every point. So we can say that, okay, infinity to r, the only changing quantity is 1 by r square dr. Right? So the only changing quantity is the r. Now how do we integrate 1 by r square? It's very simple. Again, 1 by r square can be written down as r raised to minus 2 or r square inverse. So if I can write it down like this, then simply r raised to minus 2 when integrated will become r raised to minus 2 plus 1 divided by minus 2 plus 1, which is nothing but r raised to minus 1 divided by minus 1, or simply it can be written down as minus 1 by r. If you integrate 1 by r cube, you will get minus 1 by r square. If you integrate 1 by r raised to 4, you will get minus 1 by r cube. Like that, you can integrate any quantity. So again, when you integrate 1 by r square, you will get minus 1 by r. So upon integrating, we will get the final result as gmm into 1 by r. There is a minus sign, I'm going to put it here. So minus gmm into 1 by r. In the limits, you can put the limits in the bracket actually, 1 by r and upper limit which is r, lower limit which is infinity. But you can also put the limits like this, both are fine. Whichever one is comfortable for you, you can go for that. So the upper limit is r, the lower limit is infinity. So from the limits infinity to r. So if I write this now, then I can say that, okay, it will be minus gmm into upper limit minus lower limit. You just have to substitute the value to the changing quantity, which is r in this case. So 1 by r minus 1 by infinity. What is 1 by infinity? 1 by infinity is nothing but 0, because imagine 1 by 10, it is approximately equal to 0.01. 1 by 100, it is equal to 0.001. 1 by 1000, it will be equal to 0.0001, right? And like that, if I do 1 by infinity, it will be approximately equal to 0.0000000, which means it is approximately equal to 0. Right, and the only remaining quantity is 1 by r, which means I can write this particular quantity as, that is, work done. Work done is equal to negative gmm divided by r. We got this particular result. So sir, this is work done. What about potential energy? Again, I told you, work done is stored as potential energy. In this particular case, it is against gravitational force, so we call it as gravitational potential energy. So if you are asked to find out what is gravitational potential energy of Earth, you can do this particular derivation and say that, okay, this work done is actually equal to gravitational potential energy U, that is equal to negative gmm divided by r. So you get the final result. So it's that simple. You only have to do one small integration and you will get the result directly. You just have to assume that, okay, it is the work done, and work done is given by f dot dr. Theta is equal to 0 degrees, so cos theta is equal to 1, and again f dr is nothing but the force here is gravitational force. You substitute that Voila, out comes the equation. So since we have proved that the Earth has a gravitational potential energy, we'll now learn to escape Earth. Since I'm troubling you with all these formulas and you hate me so much in the class that you decided to launch me to outer space. That is, if this is Earth, I am here, I am standing here. All my favorite students say that, sir, we don't want you here, you're too disturbing. We are launching you to outer space. So they decided to throw me to outer space or launch me into outer space in a cannon or something. So how can they launch me to outer space? So to go to outer space only, I need some velocity. So that particular velocity to escape Earth's gravitational pull is known as escape velocity. So again, if they push me at, let's say, 10 kilometers per hour, will I go to outer space? Not exactly. If they give me 100 kilometers per hour, will I go to outer space? No. That is why even if you shoot bullets that is traveling really, really fast up into the air, it is not going into outer space. Have you ever imagined that? You might have seen that people shooting random bullets into the air. What happens to those bullets? It will just go up really high, and after some time it will lose that initial kinetic energy, and slowly it will turn and will fall down under the influence of gravity, accelerating at 9.8 meter per second square. So it is coming down. That is why a stray bullet will actually be more dangerous than being shot at. Again, so if you want to launch me into outer space, you want to get rid of me forever, what speed should you actually opt? So we are actually going to try this to find out what speed should you actually have in order to get out of Earth's gravitational field so that you can go into outer space. So it's very easy. We are going to calculate what is the escape velocity required to escape Earth's gravitational field. So for doing this derivation, you can do it two different ways. Both are very similar. No difference is there practically, but you can use any one of these methods you want. Either you can do it according to the binding energy. Like, okay, let's talk about binding energy. So what is binding energy? Binding energy. So binding energy just means that it is the energy required to escape Earth's gravitational field. So binding energy just means that the Earth will be trying to bind us to it. Earth will be trying to use its gravity to keep everything together. So if we want to escape Earth's gravitational field, we have to have at least the energy that is equal to binding energy. If I am moving with a velocity v, then I have to say that my kinetic energy should be at least equal to binding energy or more than binding energy in order to escape Earth's gravitational pull. It is the energy required to escape Earth's gravitational field. It's just a fancy word, binding energy. You might have heard this in chemistry and all. But again, to keep anything really close by in its particular field, you need binding energy. If you want to escape that particular field, you need at least enough kinetic energy that is equal to this particular binding energy. You can take that particular concept, or you can say that since gravitational field is a conservative field, which means the work done in a conservative field is zero. In a cyclic process, it is zero. So in those particular cases, or you can say that conservative fields or conservative forces are the forces which is path independent. That is, if I take path from point A to point B, I had explained this in the class, I hope you remember, but still, path A to B, it is path independent. If I go like this also, it is same. If I go like this also, it is same. That is what a conservative force is. For example, gravitational field, electromagnetic field, all these fields are actually conservative fields. So what is non-conservative fields? Like those are path dependent. It actually depends on the path we are taking. For example, frictional force. Frictional force is actually path dependent. Viscous force, honey that is flowing down. All this is actually path dependent. So those who are actually path dependent is known as non-conservative forces, which are path independent is known as conservative forces. It's again explained in detail in the class, so I don't think I have to explain it again and again. But since you don't remember or you might have forgotten, it's much more easier to remind you with a quick refresh. So it will be path independent. The work done in a cyclic process will be zero, and An example would be gravitational force or electromagnetic force. All these forces will be an example for conservative fields. So again, why did I say this? Because in the presence of a conservative force, in this case it is gravitational force, in the presence of a conservative force, the total mechanical energy of a system remains constant. So we can use the mechanical energy constant thingy we learned in the previous chapter. So we can actually say that, okay, Ke plus Pe will be equal to a constant. Or we can just say that Ke will be equal to minus Pe. Like that also you can actually say that there won't be any change produced. So since that is the case, I can either use this equation or this equation in order to find out what is the minimum velocity required, because I'm going to use half mv square. That v is what we are going to use to find out what is the velocity required. So I can use either this equation or use the concept of binding energy. If you write both the cases, it is right only, don't worry. Whichever one you feel comfortable with, you can choose that. So I'm going to assume that, okay, escape velocity is indicated by v subscript e, since it is escape velocity. So now, in order to escape Earth's gravitational pull, we need an energy that is at least equal to Earth's binding energy. I say that our kinetic energy half mve square. So since v is here, escape velocity ve, we say that, okay, that is equal to half mve square. That should be at least equal to the binding energy of the Earth. That is simply the force that Earth needs to keep us together in this particular surface, right? The minimum energy we need to escape Earth's gravitational force is known as binding energy. And we just found out what that particular energy was. That is nothing but potential energy, or simply gravitational potential energy. So that is why I said you can use either Ke plus Pe is equal to 0, or simply Ke is equal to minus Pe, or directly you can also say, okay, this binding energy is the thing. So both the cases I have to write here Gmm divided by R. If I'm using the mechanical concept, that is total mechanical energy is a constant, then I can say that, okay, half mve square plus minus Gmm divided by R is equal to a constant. So if I use this also, the only difference is that this particular thing will go to the other side. Automatically it will become a plus sign. Then I can say that half mv square is equal to Gmm by R, because this is a constant. So then I can apply this or this directly, I can write it. Both the cases are right. Whichever one finds your convenience, just write down the considerations and then you can begin the derivation. Now again, in this particular derivation, it is all about cancelling some things, because here m is same and here also m is same, which is the mass of the object which we are launching into outer space cancels each other out, and I can say that ve square is actually equal to G capital M into this 2 will go right here, so 2Gm divided by R. Or simply I can say that escape velocity Ve is equal to root of 2Gm divided by R. That's it. We got an expression for the escape velocity of any object. So the only thing you have to do is that equate gravitational potential energy and kinetic energy together. Then you will get an expression in terms of velocity that is written down as Ve is equal to root of 2Gm by R. So again, what does this particular equation tell us? It tells us that, okay, for this particular velocity, we don't have to depend upon the mass of the object which we are launching. Even if an elephant is being launched into outer space, even if I am being launched into outer space, even if an ant is being launched into outer space, neglecting air resistance, then we can say that it is independent of the mass of the object that is going into outer space. It only depends upon the mass of the planet, the radius of the planet, and gravitational constant G. That is one important thing you have to understand from this particular equation. But I know you're really smart. Looking at this particular equation only, you can guess that, okay, there is only one M, it is a capital M, that is the mass of the planet. So obviously we don't have to worry about the mass of the object which we are launching into outer space. Okay, so one more trick is there, that is, instead of this, we can actually modify this equation because gm by r. We already found out what root of gm divided by r was. We already know what gm divided by r square is. So root of gm by r square was nothing but small g. We found that in the previous class. So root of gm by r square is nothing but acceleration due to gravity g. So if I modify this particular equation, the only thing that is missing from this particular equation is an extra r in the denominator. So I do one thing, that is, I multiply both the numerator and denominator by r, that is r by r. R by r is nothing but 1. So even if I multiply this equation by r, it does nothing to this equation because it's completely balanced. So again, so I multiply here by r, then it becomes 2gmr divided by r square, right? 2gmr divided by r square. So then what happens? Then I can say that, okay, I know root of gm by r square is nothing but g. Then I can write this equation as root of 2gr. So this is the actual expression for escape velocity. Which of these two equations you have to use depends on the problem they are asking for the board exam. So again, you can use either one of these two equations. Either one will give you the same result, depending on if only acceleration due to gravity and radius of the planet is given, or mass of the planet and radius of the planet is given. Depends on those two criteria, then you can automatically find out what is the escape velocity of the planet. Okay, so we have to still find out what is the escape velocity for me, right? You have to send me out to space so that I don't return. Okay, so for that, I only have to multiply this quantity. So we do know that gravitational constant is 6.67 into 10 raised to minus 11. And mass of the planet is approximately 6 into 10 raised to 24 kilograms. And radius of the planet is approximately 6,400 kilometers. So if I plug in all this data, then I will get that, okay, the escape velocity of Earth is approximately equal to 11.2 kilometers per second. So if I plug all this data into that, I'll get that, okay, the escape velocity of Earth is approximately 11.2 kilometers per second. The approximation is because I'm approximating the radius and mass of the planet. So that is why the approximation is there. If you use the correct values, you will get the exact values to escape Earth's gravitational pull. So knowing this particular value is how we launch rockets into outer space. You can also launch me into outer space if you don't like me using this particular equation. And the last topic we are going to discuss in this particular session is nothing but orbital velocity. So what is orbital velocity? Since you have launched me into space, now I have to live in space. Let's say I am in space. So on my way to space, I saw a couple of satellites. One was the International Space Station. The other was the stunning natural satellite of Earth, that is Moon. So I know that Moon is actually revolving around Earth. Okay, it's actually an elliptical pattern, but let's say that, okay, it is going around in a circular pattern. For mathematical sake, for ideal case sake, I'm saying that, okay, the satellite is moving around the Earth in a circular pattern. So in that particular case, okay, what will be the orbital velocity of that particular satellite for the International Space Station, for Moon? If I am orbiting Earth, since you have thrown me out of Earth's gravitational field, if I am orbiting Earth, then what will be the orbital velocity of any satellite, or me, if I'm orbiting Earth? So again, what is orbital velocity? So orbital velocity is nothing but the velocity of a satellite around a planet, in this case Earth. So I say that orbital velocity is the velocity of a satellite around planet Earth. So how fast it is revolving or rotating around that particular planet. So we are going to find out what is the orbital velocity of that particular moon around the Earth. So how do we actually find it out? So obviously we need to find out what is the velocity. We need to know how far it is being thrown out. That is, not every satellite is actually close to Earth. Maybe the ISS, that is International Space Station, is maybe here. If you have thrown me into space, maybe I only reached even a lesser point, which is here, which is very close to Earth's surface. And the moon is actually really far away, which means you can actually fit every planet in the solar system in between the Earth and the moon. It is that far away. How do we calculate this orbital velocity for anything? So again, we have to consider what is the distance from the center of the Earth to this particular orbiting satellite. So in this particular case, for general sakes, I am taking, okay, this particular length is r. This particular length is nothing but r. But we know in actuality that it is actually radius of the planet plus h distance from the surface of the Earth. Together I'm calling it as r. You can call it as r, you can take it as r plus h. Both are completely fine. However you want to write it, you can write it. The only thing is that we should get an expression for orbital velocity. So again, you can see that we are assuming that, okay, it is spinning around in almost a circular shape, so that we don't have to bring in elliptical patterns and elliptical shapes and all that. So we are just doing simple orbital calculations. So for this object to rotate around a particular center, we know that a force is required. We have studied in the previous chapters also, right? If I am rotating a stone which is tied to a string, we know that the string is the factor that is providing the particular centripetal force necessary for this particular rotatory motion. Right? The tension in the string is the one or the factor that is providing the centripetal force, which is again providing the centripetal acceleration. You need a force to change velocity. So again, velocity is changing at every particular instant. That is because there is a centripetal force. So here in this particular case, I can say that the centripetal force is being provided by the gravitational force. Right? There is no string tied to the moon. There is only an invisible field, the gravitational field. So I can say that gravity is the factor that is providing the centripetal force necessary for this particular revolution. So I do know what is the equation for centripetal force. I do know what is the equation for force due to gravity. This is from universal law of gravitation. This is from the previous chapter where we learned that centripetal force is nothing but mv square divided by r, where this r is the radius from the center of the Earth till the satellite. So r is that particular radius. V is nothing but orbital velocity. So since we used VE for escape velocity, I am going to use V0 for orbital velocity. So let V0 be orbital velocity, and m is nothing but the mass of the rotating satellite or revolving satellite. This will be actually equal to Newton's universal law of gravitation, that is G capital M, which is mass of the planet, into small m, which is mass of the satellite, divided by r square, which is the radius square. So again, we just cut off some things. Mass of the rotating satellite from both sides, revolving satellite or orbiting satellite. Then we get the equation. Oh, we can also cancel out r and r square. So we get the equation as V0 square is equal to G capital M divided by r, or simply V0 is equal to root of G capital M divided by r. This is known as the orbital velocity of any satellite. Considering that r is the radius from the center of the Earth till we reach the satellite. So if you want, you can also use r plus h. So if you're using r plus h, then you can write down V0 is equal to root of Gm divided by r plus h, right, where h is the distance from the surface of the Earth till the satellite that is rotating around or revolving around a particular point. Okay, then again, we can also take one particular case, that is, the particular case is when h is very less than r. Because again, I told you, satellite might not be just orbiting at a particular height. If the moon is really far away, that doesn't mean that ISS, that is the International Space Station, will also be really far away. it can be very close to the Earth. That doesn't mean that any other geostationary satellites, that is fixed position satellites or polar satellites, there are different types of satellites. Those all will be at the same height. If a plane is revolving around the planet, it doesn't mean that it is really far away from Earth's surface, because the radius of the Earth is 6,400 kilometers. What if the satellite which is revolving around Earth is only 10 kilometers above Earth's surface? That is a problem, right? So because of that, we consider a special case where h is very less than r. Not very less, very, very, very less than r. In that particular case, I can say that, okay, h is approximately equal to 0. Because again, if Earth is 6,400 kilometers in radius, then comparatively 1 kilometer or 10 kilometers is very less. So I can say that this particular equation will be transformed into V naught is equal to root of gm divided by r. This is a special case in which the satellite which is revolving around the particular planet is really close to Earth's surface. That's it. So this is the special case, and this is the general derivation for orbital velocity. So again, what do we need to understand from this particular equation? The only thing you need to understand is that, again, it is independent of mass of the object. That is, it is independent of mass of the object. Even if the ISS, International Space Station, is orbiting, or the moon is orbiting, or Jupiter is orbiting, it does not matter. It is independent of the mass of the satellite which is orbiting around any planet. It only depends upon the mass of the planet and distance between the planet center to that particular satellite. So it only depends upon mass of the planet, gravitational constant, and the distance from which the satellite is kept from that particular planet. So that is the only thing you have to understand. And if you want to spot a small similarity, there is one small similarity also here. You can see that if I take this particular equation, the special case, if I take the orbital velocity v naught, the special case, then I can say that, okay, it is equal to root of gm divided by r, right? This particular special case has a lot of resemblance, one other particular equation, that is escape velocity ve, which is equal to root of 2gm divided by r. So the only difference is that there is a root 2 multiplied in the numerator. That is the only difference here. So if I take the ratio between ve is to v naught, I can simply say that, or if I take the ratio like this, that is v naught by ve, both, if I take it either ways, it will come up to roughly ve is nothing but root 2 gm by r is to gm by r, which cancels out. I can say that which will be equal to root 2 is to 1. That is the rough ratio between escape velocity and orbital velocity. Just so that you know, I have given this ratio. Maybe they can ask it, maybe they don't ask it. But I hope you have understood what is orbital velocity, what is escape velocity, and what is gravitational potential energy. So I hope you have understood everything I have told you here today. I'll meet you all in the next session with more news about gravity. Thank you.